the case of negative and large x. So now our saddle is positioned below the integration contour. And the relief of the function of the real part of the exponent function now is inclined in the opposite direction. So now we have to move the contour down to pass it through these lowest regions along the relief of the exponent function. But here, however, we have a special point, which is our pole, negative I. And as we move the contour trying to pass it through the saddle, our contour hooks up this pole. So, and we can't curve the pole. So what would be the correct deformation of the contour? To extract it, let's actually recall that before our whole saddle point technique, or rather steepest descent technique, was based on the local knowledge of the behavior of the exponent function. By local, I mean that we only extracted the pattern of our stationary phase line or steepest descent lines near the saddle. But sometimes, especially in problems like related to Stokes phenomenon, you need to know the global picture, namely the exact position of the stationary phase and steep descent lines in the complex plane. So let's try to draw exact lines here, because our integrand is very simple. In the exponent, we have just quadratic function of the complex plane, of the complex variable. So as usual, so we are interested in the stationary phase line or steepest descent lines, which are passing through this saddle. But now we don't want to expand anything, we just want to find them exactly. So as I mentioned earlier, we can decompose our exponent function to detach the full square as follows. So once we introduce a new variable v, it's simply minus v squared over 2 minus x squared over 2. So the stationary phase lines are defined by the condition, the imaginary part of the exponent function should be constant. So the imaginary part of the exponent function at the saddle, meaning when v equals 0, is equal to 0. Hence, the equation for the stationary phase lines are now transformed into the following condition on the v complex variable. So imaginary part of v squared should be equal to 0. As a result, this immediately leads us to the following equation on the v variable itself. And we get what we expected. So the imaginary point, the imaginary line, the line imaginary part of v is equal to 0 is simply this line, which just goes, this line. And the line real part of v equals 0 is the perpendicular one. So the horizontal one, as before, is the line of the steepest descent. And the perpendicular line is the line of the steepest ascent from the saddle. And notice that this steepest ascent line actually connects the pole and the saddle, which is going to be important in a second. By the way, this is a global behavior of our exponent function. For example, since the pole is positioned above this steepest descent direction, this pole lies above their saddle. So this line, it's the line of the steepest ascent from the saddle, but it's the line of the steepest descent from the pole. And now you get the hint of how the contour should be deformed. So the correct deformation would be as follows. So you make a parallel displacement of the contour. So the contour reaches the saddle along the horizontal steepest descent line, and it goes along the optimal steepest ascent line, stationary phase line, circles around the pole, goes down again along their steepest descent line from their pole, and then continues along the same stationary phase line along the steepest descent line from the saddle. So that's the correct deformation of the contour in case of negative x. And let me show you how this looks like with 3D visualization. So here on the picture, the purple plane reflects the position, the initial position of the contour, as well as the initial position of the real axis. And the blue line, the blue curve, is the placement of the contour as it passes through the real axis. The blue dot is the position of the pole, and the red dot, as before, is the position of the saddle. And here is the deformation of the contour. Now I hope you get the idea. So it's indeed the optimal path which reflects their ideology of their steepest descent method. Also, let's keep in mind that our pre-exponential function as well as the exponent function are the single-valued functions. And that means that the integral along these vertical legs of the contour cancel each other because to the left it goes upward and to the right it goes downward, and their values of all the functions are going to be the same. So effectively, their integral is decomposed into the contribution from the saddle, the horizontal steepest descent line, and the contribution from this pole, which is a simple circle passed in a clockwise direction. And let's compute these two contributions separately. First, the contribution from the pole. As you know from the complex analysis, the integral along the small circle around the pole is reduced to the residue of the integrand at this pole multiplied by 2 pi I if the pole is passed in the counterclockwise direction. If the direction is clockwise, so the result is minus 2 pi I times the residue of their integrand. This is a simple pole, and the residue is easily computed. So it gives you simply minus 2 pi I times e2x plus 1/2. Now their contribution from the saddle is going to be identical as in the case of the large and positive x. As before, the usual trade-off takes place. There will be no large factor in the exponent function, but there will be a large factor in the pre-exponential function. So the resulting integral will be reduced to a Gaussian one, simplified to Gaussian, and easily taking. So before, we just simply square root of 2 pi divided by Ix times e2 minus x squared over 2. And the full asymptotics at large negative x will look as follows. It will be simply given by the sum of the two contributions from the pole and from the saddle. One may ask the following legitimate question. So here we have two completely different contributions. One is the simple exponential e2x, which is small, but the other contribution is e2 minus x squared over 2. So it's suppressed with respect to the first one. So is it legitimate to keep the second one next to the first one? As it happened, it is perfectly legitimate. Why? because when we computed this contribution from the pole, it is exact. So there are no corrections here. So the first probably non-zero correction could be would be only the rest of the integral, so this horizontal line integral. So that is why the first non-zero correction to this pole result is simply the contribution from the saddle. That's why you can keep it. So this is our answer for large positive, large negative x. And let's write down the answer just for reference for large and positive x. And that's the full answer for our problem. Now, let's try to figure out what kind of changes will bring us the rescaling technique, where we perform such a change of variables that our large parameter is now entering our exponent function in a homogeneous way.